Hi guys, and welcome back to my channel. In this video I want to discuss, the concept of unit cells. So previously we've discussed something called order, right? And long range order. And if you remember, this just means something that's kind of symmetric in all directions and has sort of a pattern, right? So for example, an ionic solid. An ionic solid. Essentially, an ionic solid looks like you have sodium, like for example, NaCl, right? You have sodium and chlorides arranged in sort of this pattern that extends throughout space. But that's super complicated, right? Just saying it extends throughout space, it could be arbitrarily large, right? So how do we actually analyze what a sodium chloride, actual sodium chloride sort of particle will look like, right? It's not really a particle, but how do I analyze this sodium chloride structure? I take this large, thing that extends throughout space and look at the single unit that sort of repeats throughout space. Essentially, sodium chloride is this super long thing, big thing, in its actual form, but it consists of these unit cells that are just sort of repeated throughout the entirety of the space that it takes up, right? And by understanding this unit cell, by understanding this small part of, this small repeated part, I can understand the entire structure, because the entire structure is just repetitions of this unit cell. So that's the sort of motivation and why we want to understand what the reactivity or what a unit cell will look like, because it might tell us things about the actual properties of the entire structure, right? All right, so I just want to start off with a quick, actual, rigorous, definition of a unit cell. So a unit cell is the smallest unit. It's the smallest unit that, when stacked together repeatedly, without any gaps and without rotations, can reproduce the entire crystal. So this is exactly what I was talking about previously with NaCl. We take this unit cell, copy and paste it a bunch of times, exactly, without rotating, just moving it like translational, like just moving it to the right, for example, or moving it up. It's called like translation, right? We're just doing translations to this unit cell. We're not rotating it. We're not doing anything, fancy with it. And that's going to reproduce my entire crystal. I'm just copying and pasting it and moving it over, right? So that's what the unit cell really is. It's the simplest thing I can look at that basically tells me the structure of the entire crystal. So we're going to look at specifically three sort of types of cubic unit cells. And most of the time we're going to be asked about cubic. There are other types of unit cells that I'll talk about on the next slide, but I'm not going to go into them extensively because they're more complicated to do math with, right? And we're usually not going to be asked about them. So we're going to be asked mostly about these three common types. We have first body-centered cubic, which we abbreviate as BCC, primitive cubic, and cubic close-packed or face-centered cubic. And this cubic close-packed and face-centered cubic are the same thing. You can write it as CCP for cubic close-packed or FCC for face-centered cubic. So let's look at FCC first, right? You can see that in my image we have one atom at every corner of the cube. Right? One atom at every corner, but then notice it's face-centered. So we have an atom on at the center of every face. And you can see that also sort of drawn in. We have an atom at the center of every face. Okay, now we also have BCC, right? Body-centered cubic. And this, again, sort of like face-centered cubic, describes what the unit cell should look like. We have an atom at the corner of every cube, or at all the corners of the cube, right? But we have its body centered. So we have an atom at the center of the body of the cube, right in the middle, right? And then primitive cubic, it's primitive. We don't have anything fancy going on. We just have an atom at each corner of the cube. So you can sort of see that the language that how we name these types of unit cells basically describes what the unit cell is, right? Face-centered means that there's an atom at the center of each face. Body-centered means that there's an atom at the center of the body of the cube. Primitive just means there's nothing fancy. It's just at the corners. Okay, so these are all sort of like the types of, they're called Bravais lattices, right? And these are all the types of sort of unit cells that can be represented as like a parallelogram type thing. So essentially, what these lattices are just, say we had three vectors in space, right? A, B, and C, for example, right? When we have three arbitrary linearly independent vectors, we can sort of connect them, add them, and make this sort of parallelogram, right? We can make some sort of parallelogram with with any three linearly independent vectors in space, and this parallelogram can define a unit cell, right? If I take this parallelogram, copy and paste it over, and then copy and paste it over, and stack it on top of each other, we end up getting, a unit cell that could describe an extensive crystal lattice. So basically, this term, these lattices, just mean any A, B, and C that are linearly, we take any A, B, and C that are linearly independent, form a parallelogram using them, and then use that as our unit cell. But what we focus on specifically is the cubic parallelograms. Right? These cubes are subsets of our parallelogram, or this isn't technically a parallelogram, it's a parallelepiped because it's in 3 dimensions. But we focus on cubic structures where A, B, and C are all nice, right? We have A, B, and C all at right angles, and they're all the same length. And that's going to create a cube, right? If we have A, B, and C at right angles, and we have them all the same length, we have a cube. So that's what we end up focusing on for the purposes of this, video series, because they're much easier to analyze, and and these are sort of overly complicated for our purposes. Okay, so first thing, the very basic thing is we want to talk about how do we count atoms in a unit cell, right? So let's talk about how we just count atoms in a unit cell. This is really sort of simple, but a lot of people make mistakes with this, and this comes up on basically every USNCO test. So it's absolutely necessary to know how to count atoms in a unit cell and not get confused. Okay, so let's look at, for example, a corner or vertex. So if we take an arbitrary unit cell, right? We take some arbitrary unit cell, then we have an atom at the corner, right? How many sort of atoms actually, how much of this single atom actually belongs to this single unit cell that I'm talking about? If you draw this unit cell, right, and you draw how it's going to be stacked in a crystal lattice, you're going to notice that every atom on the corners is actually shared by 8 different unit cells. So this is sort of hard. I would recommend that you draw it out yourself, right? If I take an arbitrary atom at the corner, so I'll try and draw it out. Say we have this atom at the corner. We also have the unit cell to the bottom. We have the unit cell to the side, right? So we have these unit cells that are all sort of sharing this atom. We have this unit cell at top, and then we have a unit cell, because these are 4 unit cells where such that this corner atom is belonging to it, but it's to the back of the unit cell in my perspective that I've drawn it. So if we draw the unit cells on the other side, right, we'll have it such that this atom is being incorporated into the unit cell in the front of the unit cell. And back, I'm talking about into the page. Front, I'm talking about sort of out of the page, but not really, right? This is kind of hard for me to describe. I would recommend that you draw this, right, yourself. But essentially, I can make this corner of one cube the center of 8 of these cubes stacked together, right? Such that this corner is shared by every single one of those cubes. So essentially what I'm trying to say is that this one atom is being shared by 8 cubes. So how much actually belongs to one cube? Only 1/8. So we see that the corner or vertex atom, a corner or vertex atom, is actually, in one unit cell, is actually only 1/8 of an atom belonging to that unit cell. So this is important, right? Because if you just counted that atom as one atom, you would get a wildly wrong answer because it's actually 1/8 of an atom, right? So let's look at another example, right? And I think the other examples are sort of easier to visualize. Say we have one on the face, right? We have an atom on the face of a cube. So let's draw that out. Say, you can see I put the atom here on the face of the cube. This is shared by a second unit cell that shares this face, right? You see, I've drawn two unit cells that share that common face. So this atom is shared by two unit cells, which means that one unit cell only owns half of the atom, right? So that's why we have a face atom being actually worth only half of the atom. Next, let's talk about the edges, right? So we have a similar idea for every single one of these, counting methods, right? It's how many unit cells are sharing that edge, how many unit cells are sharing that face, how many unit cells are sharing that vertex, right? So if we look at an edge, right? And I, again, recommend you draw this out yourself, but you'll see that there's actually 4 unit cells that share this same edge, right? There is 4 unit cells that share this same edge, and I'm drawing it very rough, but essentially 4 unit cells share the edge, so that one atom is shared. So how much of that atom is owned by one unit cell? Only 1/4 of it, because 4 unit cells are sharing it, and they're all equal. And then finally, say we have an atom at the center of a unit cell, right? This is the easiest one to deal with, because if you have an atom at the center, right, it can't be owned by any other unit cells, because there is no other unit cell that sort of encapsulates the center, right? All the other unit cells are outside, or are stacked, on top or to the side of the unit cell. So it's not being shared with any other unit cells, so that center atom is just one atom. It's exactly what you would think, right? So now let's do like a little question, right? And this is a very common question that shows up on a bunch of USNCO USNCO tests, but this was one I found that I thought, would be helpful to just go over. So we have a tetragonal unit cell of white tin. So tetragonal doesn't really matter. All we need to know is to look at it, right? Each circle represents a tin atom, with the gray circles sitting on the 4 vertical faces of the unit cell. So the gray circles are the 4 vertical faces of the unit cell. So they're face ones. They're sitting on the faces. How many tin atoms are contained in this unit cell? So we have 8. You can see we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 tin atoms at the corner. But remember, this doesn't just mean 8 tin atoms owned by this unit cell. Each corner is shared by 8. So we have 8 times, but the unit cell only owns 1/8 of each corner atom. So we have 8 times 1/8, which gives us 1 for the corner. And then for the faces, remember that each one is owned by, or each face is shared with 2 unit cells. So 1 unit cell will own half of a face atom. And we have 4 tin atoms on the faces, right? So we have 4 times half an atom, which gives us 2. And then, right, finally, we have 1 at the very center. Right, you can see this. It's kind of hard to see, but there's 1 tin atom at the very center. And remember, center atoms are not shared with any other unit cells. So that just adds 1 atom. So in total, we have 1 plus 1 plus 2, which gives us 4 tin atoms contained in this unit cell. So it's important to not just, if you just added everything up, you did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, you would just get 13, right? If you just added all the tin atoms up. But that's not correct, because these tin atoms in the unit cell, we got to think about how much of the tin atom is actually owned by that single unit cell, right? Because there is sharing that can happen. So this is, this always shows up on every test, and it's, it's an easy, very easy point to get. So don't miss this point. Okay, so now I want to talk more about, properties of these different unit cell structures, right? So we mentioned primitive cubic, body-centered cubic, and face-centered cubic, and now we're just going to go through each of these and look at properties of them. And the first property we're going to look at is packing efficiency. So packing efficiency means, what does packing efficiency mean? That means how much of the atom, how much of the sort of, how much space is the atom containing relative to the actual entire unit cell. That was kind of weird. That's kind of a weird way of describing it, but what I mean is how much space is the atom taking up relative to the entire space of the cube, right? So if we think about a primitive cubic structure, if I drew this more accurately, this edge length, right? What's going to happen is these atoms are basically going to touch. So we have two atoms. If we look at, for example, this bottom edge, these atoms are going to pack such that they touch each other, right? Such that the radii touch each other. And what does this mean? This means that we have one radius there and another radius here, which means that the edge length of the cube is 2 times the radius of the atom, because the edge atoms are touching each other. And what is packing efficiency defined? Defined as packing efficiency is basically how much space are the atoms taking up over how much space is the entire volume of the cube. So how efficient is my packing, right? So the atom's volume divided by the volume of the cube. And remember, how many atoms do we actually have in this structure? Everything is a corner atom, and that means everything is worth 1/8 of an atom. We have 8 1/8 of an atom, which gives us 1 atom total. So our total sort of volume of atom in this cube is 4/3 pi r cubed, right? This is the volume of 1 atom. And then we want to divide this by the volume of the total cube, which is, remember, the edge length is 2r, so we have 2r cubed. That's our, total volume of the cube. And if we do this math, we get that this results in 52.4% packing efficiency. That means only a little bit above 50% of the space in that unit cell is actually used by the atoms itself, right? Only a little over 50% is actually being taken up by this space of the atom if we model the atoms as spheres, right? So now we're going to do the same analysis, but with face-centered cubics and body-centered cubics. All right, so now we're going to do the exact same thing we did with primitive cubic, but with a body-centered cubic structure, right? So we're essentially, again, going to take the same steps. We're going to ask ourselves the question, how do I represent the edge length of the cube by the radii of the atoms, right? How do I represent that? And then I can do the atom's volume divided by volume of the cube, right? But I need to figure out how can I represent this side length by the radius of the atoms. And in this case, we don't just have sort of the primitive cubic, like them stacking side to side like that, but instead we look at this body diagonal, right? When we have this body-centered cubic stacking structure, and we want them to be as close as possible together, what happens is the body diagonal is actually where these sort of the atoms pack the closest together, right? So essentially we get one radius from the corner, each of the corner atoms, so we get 2 radii total. And then we have 2 radii from the body atom, right? So in total, 4 times the radius of the atom is equal to our body diagonal. Okay, so we're just asking ourselves, how do these atoms have to stack in order to actually create the structure? And to create the structure, we need to sort of look at the body diagonal and see how they sort of connect along the body diagonal, that they touch along the body diagonal. And with face-centered cubic, we'll do the same analysis, but we'll see that they need to touch along the face diagonal, right? So let's look at body-centered cubic first. We have 4 times the radius of the atom is equal to the body diagonal, and by Pythagorean theorem, that means the edge length is equal to 4 over root 3 times the radius of the atom. That's just simple Pythag, going from the body diagonal to the length of an edge. And now we want to find packing efficiency, which is the total volume of the atoms divided by the volume of the cube. So the side length of the cube is 4 over root 3r. So we have that side length cubed on the bottom. And the volume of the atoms that, if we take the total volume of the atoms in the unit cell, remember that we only have 2 atoms total because each of the corner atoms are 1/8. So we have 8 times 1/8 for everything on the corner, plus the 1 in the center, gives us 2 atoms total. So 2 atoms times our volume of 1 atom, which is 4/3 pi r cubed. So if we do that 2 atoms times 4/3 pi r cubed divided by the volume of the cube itself, we get 68.0% packing efficiency. And you note that this is quite a bit higher than the primitive cubic packing efficiency of just 52.4%, and we'll see that the FCC packing efficiency is even higher than this one in the next slide. Okay, so now we're going to do the same exact thing with FCC, so you'll see the same procedure, right? We're going to look and see how these atoms must stack in order to form FCC. Then we're going to look at what is the edge length in terms of the radius of the atom, and then do the volume of the atoms divided by the volume of the entire cube. So with the so now we get to look at the face diagonal, right? I sort of hinted at this in the previous slide, but we look at the face diagonal and see how they must connect, right? How these atoms must join together. We have one radius from the corner of the face, another radius from the other corner of the face, and 2 radii from the middle of the face atom, right? So we have 4r being equal to the face diagonal now. And again, by Pythag, we know that that means that the edge length, the length of the cube, or the edge length of the cube, is equal to 4 times the radius of the atom divided by square root of 2. So we have this is the edge length. And now we do the same exact calculation. Packing efficiency is the atom's volume in total divided by the side length, the edge length cubed, right? So we have 4 over root 2r cubed on the bottom. And the number of atoms with an FCC is we have 4 atoms total, right? We have everything on the corners gives us 1 atom, but we have 6 atoms on each face, and remember the faces are half an atom. So we have 3 from the faces, plus 1 from all the corners gives us 4 atoms total, right? So we have 4 atoms times 4/3 pi r cubed to give us the total volume of that the atoms take up, and that divided by the edge length cubed. And if we do the calculation, that comes out to a 74.0% packing efficiency. And one important thing to note is that this is the highest packing efficiency out of the cubic structures, right? FCC is the highest packing efficiency. And remember, FCC is the same thing as cubic close packed, right? And that's what close packed, right? It's packed closely. But close packed structures have the highest packing efficiency. It's in the name, right? Because they're packed the closest together. Okay, so now we want to sort of introduce the notion of holes in these structures, right? And holes are important because essentially we have a unit cell of, for example, let's think about like NaCl again. Essentially what happens in NaCl is one of the ions will form the basic unit cell, like the basic body-centered cubic or the basic face-centered cubic or something like that, right? And the other ion is going to fill the holes of this unit cell. So to understand the structures, we not only have to understand the BCC, the FCC, the primitive cubic, we have to understand where are the holes in this unit cell, where can the other ion sort of pack inside of the unit cell. So essentially, ionic solids will form these unit cells such that the bigger ion, which is usually the anion, will fill up the unit cell, and the smaller ion, which is usually the cation, will fill these holes. So there's a couple types of holes we want to talk about, and I'm going to start with cubic holes. And eventually in another video, we're going to see how ionic structures actually form, and some really common types of ionic structures, and which cations fill which holes, and which anions create which unit cells. So it's going to all come together kind of nicely to describe the structure of ionic solids. First, let's just talk in general. Let's talk about cubic holes. So cubic holes are found at the center of primitive cubic cells. And what does that mean? That just means they fit along this body diagonal, right? So we have these primitive cubic cells, and right in the center, we're going to have a cubic hole, right? And we talked about how the edge length before. The edge length of a primitive cubic cell is 2r. So if I look along the body diagonal, right, the body diagonal in total is going to be √3 times the size, my edge length, right? √3 times 2r. So in total, my body diagonal is going to be 2√3r, which is what I've written here. We have 2√3r is going to be my total body diagonal. But along the body diagonal, I only have 2r being taken up by the radius of the atoms themselves that form the primitive cubic structure, right? So in between, like if I sort of drew this bigger, right? We have 1r there and we have 1r here, but in between we have the total body diagonal minus the 2r that's taken up by the corner atoms. So 2√3 minus 2 times r. That is sort of the amount of space we have left along the body diagonal. And that means that amount of space can be the same thing as the diameter of a little sphere in that sort of along that body diagonal, right? If I drew a little sphere along that body diagonal with this diameter, it would fit perfectly inside that cubic hole, right? So if this is the diameter, that means the radius is that divided by 2, which gives us √3 minus 1 times r. And this is approximately 0.732 r. So essentially, when we have something that's the bigger atom is going to have radius r, the bigger atom that fills the unit cell is going to have radius r, and if we have a cation, for example, that has approximately 0.732 r, that has a radius of approximately that, it's going to fill these cubic holes in a primitive cubic lattice. And we'll see examples of this later on. I just want to do the math and show you why this math makes sense, right? All we're looking at is geometry. We're looking along the body diagonal and seeing how much empty space is there. How much diameter can I fit? And looking from that diameter, seeing what is the radius of the sphere that can fit there. And that's all I'm doing, right? And now we're going to look at two other types of holes. One is tetrahedral and one is octahedral. We're going to get to both. So let's continue. First, I'm going to look at an octahedral hole, right? And these octahedral holes are found at the center and the edges of FCC cells. Center and edges of FCC cells. So you can see that these bigger sort of gray atoms are building the FCC unit cell, and these small sort of yellow balls are building the octahedral holes. They're filling the octahedral holes, right? So if we look at how many octahedral holes are there in an FCC lattice, right? We have 8 octahedral holes that are on the edges, 8 on the edges, and we have 1 in the center, right? We have 1 center, oh sorry, not 8 on the edges, we have 12 on the edges, right? We have 12 edges in a cube. That was a little miswrite on my part. We have 1 on the center and 12 on the edges. right? And remember, edges are shared, they're shared by 4 different unit cells. So each edge octahedral hole is really just 1/4. So we have 1 from the center plus the 12 times 1/4, which gives us 4 total octahedral holes. Okay, so now how do we actually solve for the radius of these octahedral holes, right? Remember when we had FCC lattices that we said that this total edge length is equal to 4 over square root 2 r, right? And if I look at sort of how the guys on the edges are going to pack, we're going to have 1 r, if I drew this a little bigger, we're going to have 1 r here from one corner and another r from the other corner. But the entire unit cell edge is 4 over root 2 r, right? So we want to figure out how much space is in between, and that's going to give us the diameter of our octahedral hole. So we have 4 over root 2r minus the 2r that's already filled by the 2 atoms on the edges, on the vertices, right? And then that's the diameter of the sphere. So if we divide that by 2, we'll get the radius of the octahedral hole. And when we do that math, when you plug in those numbers, we get that we have root 2 minus 1 times r is our diameter, which if we simplify root 2 minus 1, calculate that, we get approximately 0.414 r. So you can see that compared to the cubic hole, these octahedral holes are smaller. So if we have a smaller cation compared to the anion, they're going to fill octahedral holes rather than the cubic holes, right? So you can see how, maybe if depending on the size of the cation, it's going to fill different holes because these holes have, are for example, these octahedral holes are smaller than the cubic holes, right? Now the last type of hole I want to discuss are the tetrahedral holes, and these I think are the most confusing, especially for me. But how I like to imagine them I imagine them as cubic holes. They're basically like cubic holes in the 8 sort of smaller subcubes that build up the FCC cell. So for example, you can see if I broke this big cube into 8 smaller cubes, right? You know how you can break any of a big cube into 8 smaller cubes by basically halving all the edges, right? Then I form 8 smaller cubes, and then I look at the inside of those 8 smaller cubes, and I look at basically what a cubic hole would look like. That's what a tetrahedral hole is. So that's a lot of words, but essentially what you're looking at is a cubic hole in the 8 smaller cubes. Okay, so essentially we're going to do the same math that we did with the cubic holes, but sort of have everything because we're looking at a smaller cube. We're looking at a 1/8 of the entire cube, right? So we're going to look at the body diagonal for the small cube, right? The body diagonal for the small cube is exactly half of the body diagonal of the entire cube, right? Because if you just sort of draw a line, you can see that the body diagonal of the big cube is going to be double the body diagonal of the small cube. So if I wanted, how do I figure out the body diagonal of the big cube? I know that, remember, this is an FCC lattice, right? So I know that this guy, the edge length, is equal to 4 over square root 2 r. But I also know that the body diagonal is equal to square root 3 times the edge length. So root 3 times a, or root 3 times 4 over root 2 r, will give me the body diagonal. And that's the math you can see that I'm doing right there, where I have body diagonal small is the body diagonal of the big cube divided by 2, which is equal to root 3 times 4 over root 2 r divided by 2, right? And that ends up getting me root 6 r if you just expand out those radicals, right? So root 6 times r is equal to the body diagonal of the small cube. Now, what is the actual radius of that hole? Remember, if I let's just go back to thinking about cubic holes, right? We have 2r from each sort of opposite corner. Remember, we're just thinking about cubic holes. We had 2r's from the opposite corners. So I want to take the body diagonal of the small cube minus that 2r from the atoms on each opposite corner. That should give me the diameter that's sort of open as a whole, right? So body diagonal of the small cube minus 2r gives me the diameter. And then if I take that, divide by 2, I should get the radius. So the radius of the hole is root 6 minus 2 over 2r. And if you plug that into your calculator, you'll get that that is 0.225 r. So basically with the holes we've been talking about, we've been getting smaller and smaller and smaller in size. And in the next slide, we're going to discuss, which size cations, for example, will fit into which holes, right? Because the smaller cations might fit into tetrahedral holes, while the bigger ones will fit into octahedrals, and the even bigger ones are going to fit into the cubic holes. Okay, so this is sort of what I've been talking about all along, which holes are going to be filled, right? And as I discussed on the, at the end of the previous slide, these tetrahedral holes are the smallest. Then we have these octahedral holes being a little bigger, and then cubic holes being the biggest. And the hole that's being filled is going to depend on the size of the ion that is filling the hole, right? Which makes sense. If something is bigger, it's going to fill a bigger hole. If something is smaller, it's going to fill the smaller hole. So here is sort of the radius ranges, because nothing is going to be, it's not going to be exactly, every ion isn't going to be exactly, 0.732 r that fills the cubic hole. It's going to be, somewhere in the middle. So the radius range is sort of not exactly the values we're going to calculate, but or that we calculated, but it's a little bit off, but it's essentially this around that range, right? So for example, for a cubic hole, we have that any ion that's around 0.732 to 1 r, right, is going to fill that hole. With octahedral holes, we have 0.414 to 0.732 r. And with tetrahedral, we have 0.225 to 0.414 r, right? So essentially these are the radius ranges of the ions, of the, for example, cations generally, that are going to fill those holes in the anion unit cell structure. And some sample compounds we have with we're going to go over these types of compounds in more detail in a future video, but just, as a little hint to what we're going to be doing, some sample compounds, for example, that fill cubic holes is cesium chloride. We have basically a structure of chloride anions, but the cesium fills that cubic hole in the center of the primitive cubic structure. NaCl, we have octahedral holes being filled. We have an FCC lattice of chlorides, and we have these octahedral holes being filled by your sodium cations. Zinc sulfide fills the tetrahedral holes. So you're going to have zinc filling the tetrahedral holes of your sulfide anions in a FCC lattice. So it's just some, interesting sample compounds, and these are very classic. Basically, you call the cesium chloride structure, or anything that takes up the form of cesium chloride, as the cesium chloride structure, right? It's so famous that the structure is basically named after that compound, right? Anything with that unit cell structure and that hole filling is called cesium chloride structure. And this is all just dependent based on, right, the radius of the cation versus the radius of the anion. The smaller that ratio is, the more likely it's going to fill tetrahedral holes. The bigger the ratio is, the more likely it'll fill cubic holes. And in the middle, it's going to fill octahedral holes. And then lastly, we talk a little bit about coordination number. Coordination number just means how many ions is it sort of directly connected to. So if we look at something in a cubic hole, right? We look at something in a cubic hole, we have a BCC, basically unit cell. So we have eight atoms on each corner, or technically it's one atom in the entire unit cell, but 8 atoms along the corner. And we have one guy in the center. This guy in the center is connected basically to 8 different ions or 8 different atoms, right? It's bonded to all 8 of these guys equally. So we say the coordination number is 8. Octahedral, you'll end up with, it's just the same as octahedral VSEPR geometry, basically. You'll end up with looking like something like this, where you have, an octahedral type shape. And obviously this coordination number is going to be 6 because you have the center guy connected to 6 atoms. And tetrahedral is going to be 4, just like tetrahedral VSEPR geometry, right? You have one guy being connected to 4 different other atoms, so we have a coordination number of 4. All right. There are some assumptions with this model, like this is not a perfect way of modeling an ionic structure, right? Nothing we've done is sort of perfect, right? Because we've assumed a bunch of things along the way. We've assumed that these ions, right? Some things we've assumed is that these ions are basically spheres of fixed radii. They're basically hard spheres, right? We've been assuming that, okay, we can take the volume as 4/3 pi r squared, and it's going to pack, directly, it's going to pack right next to each other, right? We've been looking at it basically as spheres that pack right next to each other. But this is obviously not always true, right? And additionally, we've been talking about this in a purely ionic attraction way, right? We're talking about these hole fillings and this unit cell in a totally ionic way, right? We're talking about, okay, there's just this purely ionic attraction between these ions, right? Whereas ionic, some of these ionic or quote-unquote ionic structures can have covalent character. And for example, this simple sort of sphere packing model will break down with ionic solids with high covalent character. An example of this is nickel arsenide. So if we look at the structure, this is the structure of nickel arsenide. We have these nickel 3+, which is really, really highly charged. And what that means is that it can polarize your arsenide anions very well, right? When we have a cation that's very highly charged and an anion that's very diffuse, like arsenide, right? We can end up having basically almost a covalent bond. We have this really, really highly charged cation and this anion that's very big and sort of diffuse, and it'll pull the strongly polarizing cation, it's going to pull the electron cloud and almost form like a covalent bond. And because of this, right, this structure attempts to maximize covalent bonding, not just attempting to maximize ionic attraction. So because of that, we end up with not a simple sort of sphere packing model, we end up with this weird structure. Because this structure is not attempting to maximize ionic interaction, but it's attempting to maximize covalent interaction. We're actually trying to form the most covalent bonds. And that's why you have this much weirder sort of structure that's happening here that we haven't really talked about. So what's important to note is that there are exceptions to this model. And that sort of arises from not pure ionic electrostatic interactions. Okay, the last thing I want to talk about is Bragg's law, and this, relates very well to unit cells in general. But it's basically asking the question, how do we calculate, the distances of the edge lengths of the unit cell to begin with, right? Say we have some compound, and we want to figure out what is the edge length of the unit cell, right? And we know it's a perfect cube and everything is nice like that, right? How do we figure out what is the edge length of the unit cell? And this picture, I think, is extremely nice to visualize what Bragg's law is actually doing. Essentially, we put some X-ray on our sample. So we can see that these cubes, right? We can see these lattice points. These are like our lattice points. These are our atoms, right? And our goal is to calculate this distance between the lattice points, right? Essentially, we take X-rays and we shine them at our lattice, and we shine them at a certain angle, So we see this theta, right? That's the angle we're shining these X-rays at. And we're gonna sort of sweep this X-ray through all the possible angles. We'll go from like 0 to 90, right? And what we're gonna see is when does constructive interference happen? So what is that? That's constructive interference. That's a lot of words, but what does that even mean? That means that basically that means that the light, if I look at a certain light wave, so let's have a certain light wave here and a light wave here. Constructive interference means that when these two light waves meet, right, when they meet such that their peaks are exactly in the same position and their troughs are exactly in the same position, right? They meet such that they constructively add. Their peaks are sort of at the same position and their low points are at the same position, so they amplify each other rather than destructive interference, where they would sort of cancel each other out. Okay, so how can we use this image to figure out when these? So essentially, I'm looking at these two light waves, right? They're bouncing off this lattice at two different points, right? One point is this top part of the lattice, and the other point is this bottom part of the lattice. And we want to figure out, and eventually these two light waves, I know it doesn't look like it, but essentially if we go a far enough distance away, these two light waves are going to meet and either constructively interfere or destructively interfere, right? And we want to look at where the constructive interference happens. Okay, and what does it mean if they constructively interfere? That means that the distance that the light waves are from each other. So basically, if I have a light wave, right? I have two light waves. The phase shift of one light wave from another has to be equal to some integer times the wavelength itself. Okay, so hopefully this makes a little bit of sense. This is a lot of waves type knowledge you have to have. So I'll give the equation in the end, but I really want to hopefully gain your intuition for this. What does an integer times the wavelength mean? That means that the wave is just shifted basically one wavelength or two wavelengths from the other wave. But remember that waves are periodic, right? They repeat after a wavelength. So if I shift something by an integer number of wavelengths, I'm not really shifting anything, essentially. Which means that when these meet, they're going to be basically the same wave, and they're going to constructively interfere, right? So what I mean to say is that if I'm shifting this light, this wave, this second wave, so if this second wave is shifted by n times lambda, where n is some integer and lambda is the wavelength, it's still going to equal a constructive interference, right? So if n times lambda is the shift, we're still going to have constructive interference because a shift of an integer number of wavelengths basically does nothing to the wave. The wave is symmetrical. The wave is periodic around an integer number of wavelengths. Okay, how much extra distance does this bottom guy have to travel? That's another question we have to ask, because the extra distance is going to cause the shift in the wave, right? And that's where this d sine theta comes in. So we can see that these two lines that I've sort of bolded here, that's the extra distance that the bottom wave has to travel compared to the top wave, right? So if I took this top wave line, I can see that that's like this bottom wave line if I just shift it to the right, and same with the other side, right? But we see that there's this extra distance that the bottom wave has to travel, and just doing some basic trigonometry, if we have that this distance between the lattice points is d sine theta is the extra distance it has to travel on one side, which means 2d sine theta is the total extra distance my bottom wave has to travel. But remember, for constructive interference to occur, we need that this extra distance be equal to n times lambda, right? Because it can't be shifted in a different amount, because if that was true, then there wouldn't be constructive interference. We need them to line up sort of like perfectly, such that there is constructive interference, which means that n times lambda equals 2d sine theta. Okay, and this is what we call Bragg's law. So essentially what we do is we shine these x-rays and we sweep the x-rays across all the possible angles. Then you go and see, okay, where did constructive interference occur? And constructive interference just means that you have an extra bright spot. Why is it extra bright? Because your waves were added to one another. So your amplitudes increased, right? Your amplitudes went up. And when you have amplitudes going up, you have extra bright spot. So we look at what angles corresponded to the extra bright spots. Now that means I know that an integer times that, whatever wavelength of light I was shining, which is in some X-ray range, is equal to 2 times d times sine theta, where that theta is the angle such that I got that extra bright spot, such that I got the constructive interference. So I can plug that sine theta in. Now I have a value for sine theta, and I can solve for d. D is going to be equal to n lambda over 2 sine theta, and I can solve for d, right? So this is basically how you figure out what the distance is between these lattice points. So for example, if I have a unit cell and I want to figure out, what is the edge length of this cell, I would do some X-ray experiment and using Bragg's law, figure out what d was. Alright, so this is basically all I wanted to talk about in this video. Hopefully this ending of Bragg's law made a little bit of sense. I know you have to have some waves knowledge to really wrap your head around it, but I hope that my explanation made it somewhat clearer to people who didn't have that background. Thank you guys so much for watching, and I'll see you in the next one.